Good morning. This is Mark Arnold, Senior Vice President of Marketing with ZAP Surgical. Welcome and thank you for joining us today for our final webinar of the Winter SRS webinar series. Held every Thursday between February 25th and today, this series did include 12 talks over 12 weeks. So if you haven't already, I encourage everyone to visit the srswebinars.com website to register and review recordings of prior webinars. And one final item of business before we get started. If you'd like to submit typewritten questions at any time during today's talk, you can do so by using the Q&A button found in the Zoom console. And time permitting, your questions will be addressed at the end of today's presentation. So without further delay, I'd like to introduce today's speaker, Dr. John Adler. Dr. Adler is the CEO and co-founder of ZAP Surgical and Emeritus Dorothy and TK Chan Professor of Neurosurgery and Radiation Oncology at Stanford University. Dr. Adler is also the inventor of the CyberKnife system and founder of Accuray Incorporated, as well as former Chief Medical Officer at Variant Medical Systems. Dr. Adler, over to you.
Thank you, Mark. Mark, you're going to let me share the screen. Okay, one moment, everybody. For everyone's edification, I want you to know that we're joined today with the president of ZAP Surgical. Okay, now I just have to give me 1 second. Who is well poised to help address any of the more technical questions anybody in the audience may have today, seeing as how the ZAP-X is as much his creation as mine. So it's a pleasure having this chance to, Mark, I want to make sure you can see my slide.
Yes, we can.
Okay. It's a pleasure having this opportunity to talk to everybody about the ZAP-X and the many things that have been accomplished over the past several years at ZAP Surgical. This being the final webinar in our series, I'll make a few shout outs, not only about what we've accomplished, but what I think many of our competitors have failed to accomplish. Although I like to sometimes wear my academic hat, today will be a touch more commercial than I have perhaps been in prior webinar series. To begin, why do we need a new radiosurgical system? It is worth reminding everybody that radiosurgery, in particular brain radiosurgery, has been around now for more than a generation, really 40 years. And yet after 40 years, what is arguably one of the greatest triumphs of modern medicine, and I mean that, something that harkens to the greatest accomplishments, such as genetics, human genetics, such as immunotherapies, such as minimally invasive cardiac valve replacement. Radiosurgery is on par with all of these things, yet has been a quiet revolution. And not only is it quiet, but 90% or more of the patients in the world with brain and head and neck tumors that would benefit from radiosurgery today are not getting it. More than 2 million patients, we have reason to believe, would benefit from radiosurgery, but less than 200,000 are actually getting this procedure. That's the problem. 30 years, and we're still not treating the vast majority of patients in the world. And we'll be talking about why and how we could do better. Now, that's not just my own observation. That's been an observation made by Jason Sheehan, who's a stand-up guy at the University of Virginia, who looked at the world in terms of gamma knife units and showed that arguably the United States and Canada had a sizable number of gamma knife units. But the minute you go to the rest of the world, including huge swaths of Asia, you are really under technologized with gamma knife units. There's a shortage of radiosurgery in too much of the world. That was his conclusion. And in fact, this nice little study in the radiation oncology literature suggested that the problem isn't just in the rest of the world, it's even present in the United States. Many areas of the United States, especially urban areas, rural areas, there's a lack of radiosurgery. And right now I'm starting a study to look at actually the whole question of equity in radiosurgery. Our underprivileged people get in our country getting access to radiosurgery the way more privileged people are. And my own experience is no, they are not. So this case is even a matter of racial equity. So why is this true? How can this miraculous procedure be so underutilized in many areas of the world? Well, let's take a look at the current standards of radiosurgery. The Gamma Knife or Cobalt-60 systems. Clearly, they've been the gold standard for more than 40 years. They do a good job. They're precise, they're conformal, but they're attached to significant acquisition costs, infrastructure bills, lots of maintenance requirements, got to reload every 5-6 years or so. And there's a heavy regulatory bureaucracy for good reasons around Gamma Knives. You don't want a Gamma Knife ending up in some bad guy's hands. Meanwhile, you have standard linear accelerators, your variant type products. They've been around for 2 generations. And while they're great Swiss Army knives, they do a little of everything. They are not optimized for the targeting needs of brain radiosurgery. And they require a lot of additional kind of manpower because they are so complex. And they're complex because they're so flexible. Flexibility gives you complexity. And that complexity really ends up posing yet another barrier to the dissemination of radiosurgery and the utilization of radiosurgery. So I always like to bring, it comes down to like all the 3 C's. There's cost, there's complexity, then there's the control. Do we have this technology in the hands of the people who control the patients? And so that's the problem. All these 3 reasons mean 90% of the world's population will benefit is not getting treated with radiosurgery. So the solution from ZAP surgical perspective has been the ZAP-X. Here you have that schematic images of it. It is the first of its kind vault-free. It frees radiosurgery from radiotherapy vaults and the control of people who have radiotherapy vaults. It doesn't have to be in the hospital any longer, does it? It is cobalt-free, does not require all the regulatory apparatus that is necessary to run safely a Gamma Knife-like device. And then lastly, this is optimized just for the brain and head and neck. We don't try to do prostate or breast radiotherapy. In fact, it might be possible, but it's certainly not with our machine. So in principle, this is all about optimizing this procedure just for brain and head and neck procedures. And that's where we intend to make our mark. Fix the problem of 2 million patients a year who don't have radiosurgery access. So this is something you've never seen before, a vault-free radiotherapy device, vault-free therapeutic radiation device. It is intrinsically self-shielded. No bunker is required. That's a big cost saving in itself, but it also frees up radiosurgery to put the procedure where the patients are. And this means you can put this in the back of your office, put you in an ambulatory surgery center. It can actually, as you'll see, go in some showcase places that I think for the first time is going to open the world's eyes to what radiosurgery is and why it's such a great procedure. So here, this is something that's being built out right now at Loma Linda. It's kind of going to be quite a showcase facility. Of course, you know them also for their proton facility, but I have a feeling that this is going to turn a lot of heads. Look at how dramatic it is and how visible it is to the outside world. Patients being treated now, but this is what it looks like from the machine into the world. The world can look in and see this machine. In fact, we have this relatively dramatic looking device going inside a Shinkansen station, a high-speed train station in Japan, visible by a million patients or a million people a day, just looking and realizing that this, for the first time, radiosurgery is a miraculous treatment that we all know it to be. This is being built out right now in Munich. Again, going to be a showcase facility. Now, some of this we can argue is just kind of bells and whistles and Hollywood glitz, but there's a purpose behind this. Again, that so much of radiosurgery has been this well-kept, hidden secret. No longer. We're very proud to be able to showcase to the world what radiosurgery is and why it means so much to cancer patients and more. So kind of going through the different attributes of this technology, it is cobalt-free, very important. It uses a high output linear accelerator that puts out 1,500 rad per minute at the 450 millimeter SAD. And it uses a 3 MV LINAC. Of course, no cobalt means you don't need to worry about recharging it at 5-6 year intervals. This device is mechanically optimized just for brain and head and neck radiosurgery. It is designed to give more solid angle than you can with any other device. And you're going to see in time, it's going to even increase from what we have today. So it is optimized by virtue of these mechanical elements to give you the crossfire that ensures the steepest dose gradient. And we liken this in some ways to a gyroscope, given all the angles that is enabled by these two uncoupled gimbaled gantries. And so what this means is that we've optimized every attribute of radiation energy and radiation crossfire to give you the proverbial sharpest knife. For starters, we have 260 or more non-coplanar beams that crossfire at a common point. We have optimized the energy, so there's less lateral scatter, again, steeper dose gradient. There is a collimation system that is just almost leakless. Now, I'm exaggerating some, but the fact is that it's 50 times more effective in stopping primary scatter off the target than your typical multi-leaf collimator, 50 times. So really all you're dealing with is the beam that comes out of this axis of the central axis of the collimator, as we'll show you in a little more detail. And then lastly, by using a 45 centimeter or 450 millimeter SAD, we have less penumbra. So we have multiple different attributes, the way we fire radiation out of this device that gives us the steepest possible dose gradient. And I likened it to the sharper knife. So how is it sharper? Well, here's an example. This comes out of BNI, our flagship first customer, and which they did a beam profile across multiple different devices, ZAP-X, Gamma Knife, and CyberKnife. And you can see that this is just one specific collimator, 4 millimeter collimator, where the differences are probably easiest and most significant, easiest to measure and most significantly measured. But you can see that the steeper the dose gradient, obviously, the better the treatment for small targets. But we see here the ZAP-X is constitutes this green curve, the Gamma Knife, the blue, and the CyberKnife, the red. And you can see in almost all axes, the ZAP-X is better than all, or at least comparable in one axis to the Gamma Knife. So this is what, when you distill all the different elements of how the ZAP-X is designed, it optimizes this type of concentrated radiation, which is really what radiosurgery is about. Meanwhile, because of the extensive shielding that goes in the ZAP-X, it really delivers minimal dose to the rest of the body. And you'll see this set of curves measures different types of radiosurgical devices, from CyberKnives to linear accelerators to the Gamma Knife Perfection. And the Gamma Knife Perfection still does deliver the least whole body dose of radiation, but very closely following it is the ZAP-X. And the other devices deliver as much as 2 orders of magnitude more radiation to the rest of the body. Now, I think this is going to be of particular importance as we think about treating children. And that's something that increasingly we have more and more experience with in using the ZAP-X. And lastly, in terms of just dose concentration, I keep emphasizing how my own professor and mentor, Lars Lexell, said, when the human brain is concerned, the tools cannot be too refined. And that's something I like to think our technology embodies from its very core, from its very DNA. And so this comes from a study done by Ian Paddock, a long-time student of quality radiation delivery, very much devising the Paddock Index, and always interested throughout his career in how do we measure the concentration of radiation inside the target and measure the minimal integral dose going to the rest of the brain. And so in this an NHS-sponsored study, in which Ian Paddock was asked to measure the quality of radiation delivery in different radiosurgical platforms, he measured the size of the target versus the R50, which is a percent measure of dose gradient. And what he could show is that the Gamma knife, generally speaking, this bottom curve or straight line, had the best concentration of radiation inside the tumor and the steepest dose gradient outside. Next came a range of different technologies, starting with the CyberKnife, a series of those blue diamonds, and then there's a series of different linear accelerator type systems, variant and other elective systems, and then finally tomotherapy was up at the top of this graph. But what is striking is that the ZAP-X targeted radiation had steepest dose gradient of all, measured in a number of cases, and really on par with the best of the Gamma knife, if not better. So what we keep seeing here is a very steep dose gradient outside the target, maximal dose being delivered to the target. So here's some cases that were currently being treated or simulated with the ZAP-X. So here we have an example of multiple brain mets, which are increasingly becoming the dominant workhorse of all radiosurgery. So here we have 3 brain mets, which took merely 15 minutes to plan, 19 minutes to treat. These were all kind of simple cases, 3 isocenters in total, but delivering a relatively sizable dose of 24 gray. What you see at the end of this is that you're delivering a negligible dose to the entire brain, just 0.4 gray. And we'll talk more about that and contrast that with sort of the VMAT solution that some have posed for treating multiple brain mets. Here's an example of even more brain mets. And increasingly, this is what we are treating in radiosurgery. It used to be that, and me included, proposed that more than 3 brain mets, radiosurgery was futile. And I wrote an article about that, 25 years ago, saying exactly those words. But now, through the work of Yamamoto and others, we realized that you can make a big difference in many patients' lives by treating radiosurgically multiple brain mets, and oftentimes treating multiple brain mets over time. So one of the striking things that we see in some linear accelerator solutions is a desire to just be quick and dirty, to do a VMAT solution. And we've seen multiple presentations recently about this. And what's striking is their inability in their targeting systems to know exactly where the tumor is, and therefore to use 3 millimeter margins around the primary target. So they make sure that they cover the tumor. And then in addition, they end up smearing a lot of low dose across the entire source of the brain. Now, oftentimes giving as much as 7 or 8 gray the entire brain for a case such as this. So the VMAT solution is what we are not delivering at the ZAP-X. We really believe in, Lexell's mantra that you cannot be too refined, that good enough is not good enough in treatment of the brain. And so the VMAT solution is something, although it's fast and efficient, I wouldn't want it for my own patients or much less my family's brain. Let's minimize integral dose. And that's kind of part of the mantra of what we try to deliver with the ZAP-X. And why is it so important to minimize whole brain dose that you see with VMAT? Well, because we know about 70% of patients who get radiosurgical treatments alone to multiple brain mets are going to recur. And if they've already gotten as much as 6, 7, 8 gray to the whole brain, it doesn't give you much flexibility to retreat. It's like retreating with whole brain, never necessarily a good thing for cognitive function. So as we start thinking about where radiosurgery is headed, where we're going to treat more and more multiple brain mets, it's going to be increasingly important to treat each brain met is an isolated lesion so that we minimize surrounding dose to brain and we achieve the steepest dose gradient. And that is at the heart of what the ZAP-X tries to do. Give you that dose gradient in tumor and keep it out of the normal brain. So here, how can this dose gradient be meaningful as well? Well, here's a case of trigeminal neuralgia, just to kind of showcase the technical capabilities. There you see, very quick, fast to treat. There you see fast to plan, fast to treat. And this is really a Gamma Knife-like treatment plan with a single isocenter and spherically based. But in the end, I think you see a steep dose gradient with minimal dose going to the brainstem. Certainly at 0.07 cc brainstem dose of greater than 12 gray, you'll have no problems here. Alternatively, this is kind of the style that we did at Stanford with our CyberKnife. We treated a more elongated, non-isocentric treatment. And you could also do that with the ZAP-X, just showcasing its flexibility. Here you see all of 10 minutes to plan a case like this, 25 minutes to treat. It does involve, in this case, 2 isocenters and a grand total of 95 beams. In this case, because we're going a little closer to the brainstem, we have slightly higher V12 of 0.09 cc's, but clearly by the standards of all other radiosurgical systems, an excellent treatment plan. That's what maximizing penumbra at every element of the system gives you. So just to go through the different components, and we'll try to integrate this as a product for you. We have 2 rotational axes, a gimbal within a gimbal, and these give you this gyroscopic pattern of beam crossfire. So as you'll see in the video, these are uncoupled, and these give you the flexibility to sort of come at the target from multiple directions. Meanwhile, the mechanical elements that move the critical components in space also serve the function of shielding the radiation and keeping it within the apparatus and protecting the operator from radiation, thereby obviating the need for a radiotherapy vault. So you have this external shell and you have these vertical doors containing the radiation. But surprisingly to many, this is not claustrophobic because it opens up inside. We know with hundreds of patients that this is not a claustrophobic experience. One should think of this entire apparatus as a robot with truly 6 degrees of freedom. There's these big rotational degrees of freedom I just alluded to, and now the table has 3 degrees of freedom. And you'll see it moves with great precision throughout the entire treatment space of the eyes of the system. The targeting device uses something like the CyberKnife. It uses a KV and a KV tube and a KV amorphous silica camera, and takes these projection images and correlates them against the DRRs using standard techniques that were devised originally for the CyberKnife. But in this case, we're using a single imager and a single KV source. Finally, we have a collimation system that's best in class, which I'll be showing you a little bit more, that leads to minimal leakage off this primary target and gives you minimal penumbra. And very interestingly, for the first time ever, we have a real-time dose monitoring tool of transit dosimetry. We're not just measuring dose exit from the head of the collimation system, we're measuring it that's transmitting through the patient's head. And from now on, in a QA process, you have real-time confirmation of the dose you're delivering. You're no longer based your assumptions all on machine calibration. So if someone makes a mistake in the calibration process, we'll know and we'll be able to check it before anything bad happens to a patient. And those of us who've been around radiosurgery for a while know that some of the most horrific injuries in all of radiation therapy have been in the world of radiosurgery because machines were miscalibrated. The treatment planning system devised by Mohan, is on the call here today, is really a revolution unto itself. It represents one of the simplest devices you'll ever see in the radiosurgical world today. With a single click, you can get a high measure of dose conformality using this new inverse treatment planning system and get these sort of plans in less than a minute. And it is really an amazing. Now you can then go on to modify the manual if you want to adjust things, but ultimately it's devised with the very logical underlying assumption that we should shoot for getting all the dose to the target and nothing outside the target volume. Now, obviously, it's a compromise beyond that. We're only optimizing that sort of function. But what you'll see is, I think, brilliant plans with minimal effort. And the whole UI, UX does not require weeks and literally, in some cases, months and years to learn, like systems I would suggest, like Eclipse. So now the collimation system is really cool. So here you have an example of our spinning disc, which has drilled through this tungsten wheel 8 different apertures. Literally in a second or two, we can change aperture sizes from 4 millimeters to 25 millimeters in various different increments. And this gives you throughout the procedure just infinite opportunity to change this beam size, the beam dimension. And this too is part of the secret sauce that gives us the brilliant dosimetry that I've been alluding to. The targeting system uses this amorphous silica camera that you see in the back, as well as this KV source. Together, they generate real-time images that are then correlated against digital reconstructed radiographs made from the patient's original CT. So original CT is used to generate DRRs, predicting patient position orientation. Then real-time images are correlated against that that library of DRs and allows us to establish with sub-millimeter accuracy where the patient is positioned in space. You get frame-based targeting accuracy without frames. Now, I know there's always some doubters out there, there's some frame believers, but we are convinced that you will see in time, even those who believe in frames, to say, no, I give up. I do believe image guidance is every bit as accurate as frames. Just stay tuned and be prepared to be amazed by the accuracy of image guidance today. So lastly, I alluded to this error protection real-time dosimetry. So what we look at is a measure of dose transiting the patient's head and striking this dosimeter opposite the treatment beam. This allows us with each and every dose to confirm the dose against the dose delivered against what was predicted to be delivered. So it is yet another QA tool that we think will allow ever safer use of radiosurgery and really let people who maybe have been in past intimidated by doing radiosurgery, worrying that perhaps a physicist would have a bad day and a patient would be mistreated and grievously hurt. That isn't going to happen anymore. Should a dose be delivered that's not expected, of course, the machine stops itself and the operator can intervene. So, I explained a lot about the technology here. I want to go back to sort of why is this technology important? Why are we doing all this? Didn't we arrive at the pinnacle of great treatments, with prior technologies? Well, I believe I have always been a student of Lars Leksell, and I still to this day. And I like to believe that ZAP-X reflects his ethos. And I reiterate, the tools used by the surgeon must be adapted to the task. And where the human brain, specifically the human brain, is concerned, our tools cannot be too refined. You can't take dose back to the brain once you've given it. Now, if you give a little extra dose to the liver or lung, perhaps that's, it's not the end of the world. But your dreams, your memories, your cognition is at stake every time you treat with radiation. And so the beauty of concentrating the radiation in the target to the greatest extent possible is increasingly going to be important, especially in patients with brain mets. And the chance you're not going to have multiple goes with your VMAT solution for a case in point. Meanwhile, how about the much hyped, HyperArc and your other linear accelerator systems? I was credited by Varian as creating Edge. Here I am supposedly introducing Edge to the world. And I did, in fact, I was very instrumental in creating Edge. If you look at the covers of the Edge of the linear accelerator, you can see how the lines kind of converge to a point. That is my creation to Edge. That's my contribution. And I was considered the creator of Edge. In fact, that shows you how unoriginal Edge is. Edge is just a true beam repackaged with a couple fancy lines on it designed by me to now be declared a special breakthrough product. In fact, the entire linear accelerator world is incredibly cynical and unchanging. The whole idea of hyperarc is nothing new. Hyperarc is what Winston Lutz designed almost 40 years ago, 35 years ago. It is a throwback to the past. Now, I have to admit, it's better than what they've had in the past, but there's nothing innovative here. Nothing has been optimized for brain and head and neck radiosurgery the way we at ZAP have taken all the time and money and effort to make best-in-class radiosurgery possible for brain and head and neck. We have worked hard through our innovations to be the best, because when it comes to the brain, you cannot be good enough. So here, a little video to walk you through everything you've just seen, show you what it takes to be the best. So here we are, our self-shielded device, operator sitting right next to it. This can be in the back of your office. It doesn't have to be in the basement of the radiotherapy department. There's no 4 million pounds of concrete between you and your machine, between the world and your machine. Yes, the patient goes entirely in the machine. It is not claustrophobic. And for those of you who don't believe, I urge you to get into ZAP-X soon and see for yourself. The collimation system, best in class, minimal leakage, 50 times less leakage than you get with the best in class multi-leaf collimator. This spinning disc provides the beam shaping apparatus from 4 millimeters to 25 millimeters. You can have almost an infinite number of beam changes, aperture changes. So the targeting system is X-ray image-to-image correlation using real-time digital imaging and correlating that against a digital reconstructed radiograph, against CyberKnife-like, but with a single X-ray projection over time. So the machine is a robot. Everything moves. Everything is optimized for maximal accuracy, for minimal penumbra. And here you can see the yaw and the pitch. And then you'll see the movements of this device. I liken it to a gyroscope. One rotational axis, second rotational axis. These are uncoupled from one another, and they give you much more solid angle. 2 pi steradian and even more over time. And there's all this solid angle that gives you this steep dose gradient. And that the dose gradient is at the heart of everything radiosurgery is supposed to be. So here we are over time shooting beams from many directions. And many of you will think, oh, couldn't we do arcs here? I think you'll be seeing in the next couple of years, you'll be seeing arcs as well, making treatment even faster and potentially even steeper dose gradient as well. And here's the real-time transit dosimeter. We can measure not just the dose coming out of the radiation head, but what goes through the patient's head. This is a QA tool that is revolutionary and will make radiosurgery safer in the hands of even those who haven't done that much experience with radiosurgery. So here, these are the new radiosurgical centers of the future. They are showcases for the institution. They are opportunities for the world to learn about this truly great therapeutic revolution. So that was then, and now this is next. So what do we got? No, let me get, okay. So who's ZAP? ZAP, I happen to be the CEO and founder of ZAP. We're founded 7 years ago, headquartered in Silicon Valley, initially a spin out of Varian, but also funded in part by Foxconn, the people who make probably the electronics that you're using to watch this very video right now. And Mohan Bardalari is the president who was on this call and post. I also help with technical questions here because he's much smarter technologically than me. So from a regulatory standpoint, we have regulatory cleared in much of the world, and with a little bit of luck, we're hoping to get through the final stage of our NMPA application and might have regulatory clearance by the end of this year, having just recently treated the last of patients in a 55-patient clinical trial at Beijing 301. Speaking of Beijing 301, there you can see it in the middle of the slide. These are the sites where we're currently treating patients, treating in all continents. And we're in fact just started treating patients in Miami just earlier this week. So we have a number of installations going in, and behind these, there's another 20 other machines. So you are going to increasingly see the ZAP-X around the world. All of this constellation of customers really believe that best-in-class radiosurgery is what they want for their patients. So here you go. These are additional centers around the world that are soon to get ZAP-X's over the next couple of years. And so to summarize, the ZAP-X is the first of its kind vault-free therapeutic radiation device. For the first time, we can put radiosurgery where the patients are. We don't necessarily require all patients to go to these meccas of radiosurgery. We are democratizing radiosurgery by freeing it from the vault. This technology is optimized from the ground up for best-in-class dosimetry. Delivers a sharper dose gradient, minimal scatter from the primary target, really best-in-class collimation with marked crossfire, minimal penumbra. And in the end, it's important to comment, it doesn't require the complexity of monitoring radioactive cobalt safely. This really saves a lot of time and money and really makes the world a little bit safer by having less cobalt in it. So if it wasn't enough, what our company is trying to do, I want to showcase something that's potentially even more revolutionary. And that's the idea that radiosurgery may not be just for the 2, 3, 4 million patients a year with brain and head and neck tumors that aren't getting it, but there's a big world out there for functional neurosurgery where we can transform the lives of patients with depression and addiction. And so here's an example of one of our soon-to-be study subjects at National Taiwan University. This is an addicted pig, sadly, but a happy pig. He drinks almost a fifth of alcohol a day. As you'll see, he really likes his alcohol. When given the choice to play with toys or drink water or eat food, he just goes back and drinks his alcohol as long as he can. With his little snout, he pushes a button and fills his pan with alcohol and drinks away. His life is becoming alcohol. He's an alcoholic. And as you'll see, his behavior is a lot like some of the alcoholics you may see at your local bar. Here he is, pretty intoxicated, stumbling up like someone out of a bar seat, trying to cross the bar to get yet another drink. So this is our study subject with addiction. And we are trying to show that radiation can be used not just to destroy things, not just to destroy tumors, not just to destroy brain targets, but can actually be used to down-regulate neuronal circuits, turning them down like a thermostat. So this whole concept of radiomodulation is kind of transformational. And in a range of different animals models, now starting with an actual addiction model, we're going to hopefully convince the world that radiation has its place in treatment a host of different behavioral diseases, starting with addiction. So that's what our company's doing. That's where the ZAP-X is destined. And it's been a privilege talking to you today in this last webinar series about what we've been doing at ZAP Surgical. And I'd be delighted to entertain any questions that you might have. Mohan is equally delighted and maybe even better suited than me.
Very good. Thank you, John. As John mentioned, you can submit questions now using the Q&A button at the bottom of your Zoom screen. Some of the questions that have come in so far Can you share some data regarding treatment time for treating targets with irregular shape? How many shots are required for a typical acoustic neuroma or cavernous sinus meningioma?
I'll tell you, Mohan has been deeply involved in treating lots of patients over the last couple of months, and maybe just have Mohan comment on that question.
Hi guys. So basically, we've treated a bunch of patients in China for clinical study, and we treated 55 patients. With some patients have multiple targets, so I assume the total number of targets were around 70 or so, 75 targets. And none of the treatments have taken more than 45 minutes, and there are some very complicated, funny-looking targets for sure. And the planning time itself is typically, an hour or two, and very complicated cases, maybe 4 to 5 hours. And specific cases, specific things that this question asks for, the meningiomas, I know we have done it. I'm not sure about the other one. I'm an engineer. John, you may want to comment on the specific target types.
Yeah, I mean, I think acoustic neuroma treatment time can be, less than 30 minutes. It really depends. As you know, there's various different types of acoustic neuromas. You can have a partially resected, cystic, kind of 3.5 centimeter irregular shaped lesion, and you can have a small little intercanicular tumor, which is literally a 10-minute treatment time. So I think you should expect treatment times with the ZAP-X to be as fast or faster than the Gamma knife is today. I might add a new Gamma knife, because as we know, gold Gamma knives slow down. So treatment times are not challenged at all. And you're going to find that treatment times are going to go over time, are going to get even faster and faster with the ZAP-X as we start to optimize its performance. So treatment times are, whether it be irregular shaped cavernous sinus meningiomas or partially resected acoustic neuromas, are not a challenge, as fast or faster than any other modality.
The specific question that was asked as well was number of isocenters for a irregularly shaped target. As you know, it depends on the type of the target, depends on the size, the shape, and all that stuff. But I can tell you just by looking at it, we have 8 different collimators versus Gamma knife has only 3 collimators. And our sizes vary even higher. So it'll go all the way up to 25 millimeters. So you can imagine the number of shots that we would require in a given target would be less number of isocenters for us.
Very good. The next question, it looks like there is room to treat down to C-spine. Technically, how low can you go with C-spine?
And ZAP-X is designed to treat to the base of the neck in the 95% American male. So, and if you are, an NFL football lineman, we're just going to get to the upper neck. But for your typical American, and actually for your typical human being, no problem getting down to the middle or the base of to the bottom of the neck. And it's designed to do that.
Okay. What is the total weight of the system?
It weighs a lot. You don't want it to fall on your foot. So it weighs 60,000 pounds. But you should understand that it substitutes for a 4 million pound cement vault. And so it does need to be sited on the first floor, or it needs to be sited on a ground floor level.
Okay. And a question from Lijun Ma at UCSF. Would the MV dosimeter panel have live readouts to allow checking against delivered dose in real time?
It does beam by beam. Right now, that's exactly what it does. But in time, you'll see how it's going to be integrated over time. The dose will be integrated over time, and to show the correlation over the entire course of the procedure. And eventually, we hope to even give you spatial confirmation. You can see not just how deep your knife is cutting, but make sure it's cutting the right anatomy. I keep referring this to kind of a knife, a scalpel metaphor, because that's the way we should think about radiosurgery.
So in that sense, if there is a problem with the radiation administration, we catch it at the beginning of the treatment, not at the end. Like most other safety devices we may have, they usually make the calculations at the end of the treatment, not at the beginning of the treatment. We catch it from beam to beam.
Okay. In case of a power outage during a treatment, how does ZAP-X handle the situation?
The door comes down automatically, and we can extract the patient in less than about 30 seconds. I mean, that was the time frame that the FDA required us to do it. So it's every bit as fast as your ability to get in and out of a radiotherapy vault that has this big lead door on it. So.
Okay, this is a recap question, but worth noting again. Is the ZAP-X commercially available outside of the US or Canada?
Absolutely. It's available in much of the world nowadays. I mean, we just passed a MedStap audit last week, which opens up some new markets like Canada and some Latin American countries, but it's certainly available in Europe, the United States, Japan, Taiwan, and with a little luck throughout China by the end of the year.
Okay. How is the treatment table attached? Is it attached inside the shielded sphere? Is there shielding below the treatment table?
Mohan, would you care to elaborate?
Yeah, so the whole machine is fully integrated. So that means the table is actually attached to the chamber. And there's a shell that goes all the way around. There's a door that comes up that closes up the patient. So yes, so the shielding is available all around. Now, obviously, this whole machine sits on a foundation. So we do take that into consideration in terms of providing some amount of shield.
Okay. Any comments on transitional placements, such as a trailer?
Well, because we don't require a vault, that is possible for a radiosurgical system now. And so, yeah, we've scoped out placing the ZAP-X in a trailer with a company called Kentucky Trailer. And I think one of our customers soon is going to order such a device. And so, yeah, we can go in a trailer. I've even given thoughts to becoming in my retirement, putting this in a trailer and driving around the backwoods of America, treating patients in small little hospitals. My wife is greatly excited by that idea. But the fact is, we can go in a trailer, unlike any other radiosurgical device there ever was.
Okay, what is the overall footprint of the unit? I imagine the question is the dimensions for the space to put the system.
The ideal space is 6 by 9 meters.
And how does that compare to a conventional linear accelerator treatment vault?
Well, the inner room is not too different than a general linear accelerator treatment room. What's different is that you don't have your 6, 7, 8 feet of concrete in addition around each wall. So the net size of footprint needed for a ZAP-X is appreciably smaller than your standard radiotherapy vault.
And also the operator sits inside the vault. It's also, you don't need space outside, and the equipment room is almost nothing in the equipment room. Almost all the equipment is on the machine.
Okay, any comments on the machine QA from a daily perspective?
Mohan?
The QA for our machine ZAP is almost exactly the same as any other LINAC for now. That means, you do the daily output check in the morning, and then you can treat for the rest of the day. And then you do either weekly or monthly some additional QA and semi-annual and annual maybe water phantom tests. Now, we do expect in the future, thanks to the geometry of our machine, the physics community will innovate and come up with newer and better ways of checking the beam and so on and so forth, not just depend on water, because getting the water tank inside our machine is a little bit more difficult. We made it possible because we are a new technology we wanted to prove with the existing QA method. But we do expect the physics community to come together and come up with new and improved QA techniques that will actually benefit the entire industry, because we should have gotten away from water a long time back, but there was no motivation with other machines. So I think ZAP will provide a lot of motivation for that.
Very good. We'll take
Sure.
two more questions here. John, here's one related to trigeminal neuralgia. Some major problems with radiosurgery for trigeminal neuralgia is the long latency to pain relief, the lack of dermatomal specificity, and the unpredictability of undesired V1 lesioning, leading to corneal complications. Can we expect ZAP to perform better in these respects?
Well, the truth is we don't know yet. It's going to take time, but the steeper dose gradient should work to our potential advantage. And I mean, I think the author of this question rightfully points out the limitations to radiosurgical lesioning. But I think there is no perfect procedure for the treatment of trigeminal neuralgia. MVD in the young, healthy patient with classic trigeminal neuralgia, that's probably clearly the category where the treatment is clearest. But more often the situations are muddled. Patients are older, they're less healthy, the symptoms are less classic for trigeminal neuralgia. And in these patients, radiosurgery does seem to have application. And the steeper the dose gradient, the better the treatment option, the better the treatment outcomes we can expect. So, I mean, we've treated about 200 patients to date here, so it's going to take more time to answer that question definitively, but I hope in a couple of years to have that answer.
Okay, one final question. With respect to the dose outside of the primary targets, if the nominal constraint is 0 dose, do you still define the traditional organs at risk and regions of interest? And if so, are these allocated individual constraint doses for inverse planning?
Mohan, you want to take that?
Yeah, so it's a kind of an interesting way we designed our treatment planning system, and we can do something that's very, very automatic as well as highly manual. So if you depend on the automatic solution, what it simply does is that it says that all the radiation needs to go into the target and no radiation goes outside the target. That means the question is very, very correct. There's no reason to specify constraints for all the other critical structures. Now, it also means that the question comes up, do we need to even outline or contour these other critical structures is the question. And in theory, no, you don't have to outline these structures except for to get statistics. So, you need to figure out what the minimum dose is, what the maximum dose is these targets are getting, and what is the, as given a specific dose, what volume of this critical structure is getting this particular dose. So for the statistics reason, you have to contour these things, but not for inverse planning. So on the other hand, if you want to do it manually, you can add constraints for each and every critical structure, just like you would give constraints to the targets themselves. Yeah, so we have the whole gamut. You can do it fully automatic without even thinking about what constraints you're adding, and the system will take care of it. Or you can add the constraints exactly the way you want.
Okay, very good. I think that's all the time we have. We've extended well beyond the allocated time. We'll take the remaining questions and we will do our best to respond to those offline. Otherwise, John, I'll hand it to you to wrap up.
Okay, well, I'd just like to thank the audience for participating in today's webinar. And those of you who participated over the last several months, thank you for joining us. It's been fun communicating with all of you, and hopefully you found the content and speakers that have been talking as instructive as any big medical conference that you've attended. So I wish you all well. And if any of you would like to learn more about the ZAP Surgical and ZAP-X, please feel free to reach out to me or anybody on this call. So thank you, and all stay safe. Bye-bye now.